Welcome back to Concrete Conversations, written and hosted by Texas Slab Guys. This podcast covers meaningful stories that impact the concrete industry. Today, we're talking about how Rice University scientists figured out why concrete crumbles faster near the ocean, and how we might be able to fix that problem to make buildings last longer. But before we dive into that story, please hit follow and subscribe if you want to stay up to date on concrete industry news.
So I want to start today with a piece of research that landed on my desk. It's from Rice University,
Okay.
dated November 18th, 2025, and it's written by a Dr. Raji Natarajan. And on the surface, you look at it, and it just seems like a standard engineering update. The headline is all about concrete durability.
Right, which, to be fair, usually signals a pretty dry read for anyone who isn't, a civil engineer.
That was my first thought, absolutely. But then I saw who was behind it, Assistant Professor Kai Gong and his team. And I realized this isn't really about concrete, or at least not the concrete we think we know. It's about this hidden world operating at the nanoscale that basically dictates the lifespan of our entire infrastructure.
And that is not an exaggeration. We're looking at a fundamental shift in how we understand the most consumed material on Earth. After water, of course.
We're going to get into molecular dynamics and nanopores and how a traffic jam of atoms might be why bridges collapse.
It sounds like science fiction, but it's not.
It really does. But before we get there, I want to point out why the author, Dr. Natarajan, covering this matters. She's not just a reporter. She has a PhD in cell biology.
Which is such an interesting crossover, right? A biologist writing about cement. But it makes perfect sense when you read this study. Gong's team is treating concrete almost like a living tissue.
A living tissue.
Yeah, I mean, it has a structure, it has these tiny pathways, and it has active transport going on inside it. It's not just a dead rock.
Okay, let's get into that dead rock misconception. The source talks a lot about calcium silicate hydrate. For anyone who doesn't know, this is the binder, right? The glue.
Correct. When you mix cement powder with water, you start a chemical reaction. And the main product is this gel. Calcium silicate hydrate, or CSH. It's what hardens and holds everything together.
And if you look at it, it just looks solid, uniform.
To the naked eye, absolutely.
But the whole point of this new research is that solidity is, well, it's an illusion.
It is. CSH is basically a porous sponge. It's just riddled with these incredibly tiny voids. They call them nanopores.
And these aren't cracks or defects.
No, not at all. They are an intrinsic part of the material's structure.
Yeah.
And for decades, scientists have known they're there. They've known that water and ions can move through them.
But knowing they exist isn't the same as understanding how it all works. The article says we've lacked a molecular level, spatially resolved picture.
Which is a very polite scientific way of saying we've basically been guessing.
Or at least working with a black box.
Exactly, a black box. We could measure what went in one side of a concrete block and what came out the other side, bulk properties. But we couldn't see what was actually happening inside the tunnel.
It's like trying to understand rush hour by only counting cars entering and leaving a city.
Perfect analogy. You have no idea what the highways look like.
So this is where the methodology really caught my eye. Gong and his postdoctoral fellow, Wei-Kong Shen, they didn't use a microscope. They used molecular dynamics simulations.
And this is the key. This is the breakthrough, because physically observing this stuff it's incredibly difficult.
Why?
Well, you're dealing with spaces that are nanometers wide, a billionth of a meter. If you try to slice concrete that thin to look at it, you change the sample.
Yeah.
You dry it out. You destroy the very environment you're trying to study.
So they built a digital twin instead.
Essentially, yes.
Yeah.
They programmed the laws of physics into a simulation. They built the atoms of the CSH. They added water molecules. They added ions. And they just hit play and let the simulation run.
Okay, I have to play devil's advocate for a second. How much can we really trust a computer model versus, physical data? Isn't there a risk of garbage in, garbage out?
That's always a risk, of course. But molecular dynamics has become incredibly robust. You're not just telling the computer, make the water move.
Right.
You're defining the electrostatic charges, the mass, the bond angles, the van der Waals forces for every single atom in the system. It's less like a video game and more like a massive calculator solving Newton's equations for millions of particles at once.
And the big advantage, according to the source, is just total control.
Absolute control. You want to see what happens when a pore is exactly 3 nanometers wide versus 5 nanometers. You just change one parameter in the code
You can isolate variables.
in a way that's physically impossible
Yeah.
with a real chunk of cement.
So they build this digital tunnel. They flood it with water and ions, sodium and chloride specifically.
Yeah.
And this is where we get to the core finding, the spatially resolved part.
Mm-hmm.
They found that the traffic, it doesn't all move at one speed.
And this is the nuance we've been missing.
Yeah.
In the past, our models just kind of assumed an average speed, a
Yeah.
single number. But the simulation showed this really clear gradient.
The fast lane and the slow lane.
That's a great way to put it. The
Oh, yeah.
water and the ions near the very center of the pore move pretty freely. They act like you'd expect a normal liquid to act.
Okay.
But as you get closer and closer to the walls, the solid CSH, everything slows down dramatically.
Why? Is it just friction? Like water in a pipe?
It's more than friction. It's stickier than that. It's chemistry. The surface of the CSH is charged, and water molecules are polar. They have a positive end and a negative end. So the water molecules literally form hydrogen bonds with the surface. They get absorbed.
So the wall is actually grabbing them.
It is. It's holding them tight. And this creates a layer of water that's highly viscous, almost like a structured solid itself.
Wow.
And that structured layer creates drag on the next layer out, and so on. It's only when you get to the very middle of the pore that the molecules are far enough from the wall's influence to move quickly.
And the study points out this effect is even stronger for the ions, the sodium and chloride.
It is, and this is where the villain of our story comes in.
All right.
Chloride.
Yeah.
We all know it's bad for infrastructure. We see the spalling on bridges. We hear about rebar corrosion. But I want you to connect the dots for me. Why does the speed of the ion matter so much? If it gets there eventually, isn't the damage done either way?
Speed is everything. Because infrastructure has a lifespan. We design a bridge to last 50 years or 100 years.
Right. That lifespan is basically a calculation. It's how long will it take for the chloride concentration at the depth of the steel rebar to reach a critical level.
So it's a race against time.
It is a literal race. The concrete covering the steel is a barrier. If the chloride moves quickly through these nanopores, it might reach the steel in just 10 years. That's a disaster.
Okay.
But if it moves very, very slowly, it might take 200 years. And by then, the building is probably obsolete anyway.
So Gong and Shen's simulation, it isn't just academic. By mapping these fast lanes and slow lanes, they're giving engineers the blueprint to basically rig the race.
That is the ultimate goal. If you understand that the speed is dictated by the pore width and the surface chemistry, you can start engineering the concrete mix itself to maximize that slow lane.
You could create structures with smaller pores.
Or with surface charges that repel chloride more aggressively. It moves us from trial and error mixing stuff up and waiting 20 years to see if it cracks to intentional atomic level design.
Which is becoming more and more critical. The source specifically mentions salt-rich coastal environments.
And with the sea levels rising, our infrastructure is going to see a lot more salt water, not less. We need better defenses.
This leads right into the environmental impact. The article drops this statistic that I think a lot of people just gloss over, but it's staggering. The infrastructure and construction sector is responsible for over 40% of global greenhouse gas emissions.
40%. And about half of that comes just from producing the materials themselves, concrete and steel.
And cement is particularly dirty, right?
It is. You have to heat limestone up to 1450 degrees Celsius. That takes a massive amount of energy, and the chemical reaction itself kicks out CO2.
So the most sustainable concrete is the concrete you don't have to pour in the first place.
Longevity is the ultimate form of sustainability. If we can use this new framework to, say, double the lifespan of our bridges and seawalls, we effectively have the carbon footprint of that infrastructure over time.
You stop the cycle.
You stop the build, corrode, repair, repeat cycle that we're stuck in.
It's a powerful argument, but I want to zoom out even further. The article mentions this research has implications way beyond just civil engineering. It lists things like water purification, battery storage, even nuclear waste.
And this is what really excites me as a scientist. Physics is universal. The rules that govern an ion moving through a concrete pore are the same rules that govern a lithium ion moving through a battery separator.
Okay, let's unpack the battery angle. We're all obsessed with charging speeds and EV range. How does this wet rock simulation help my phone charge faster?
Think about what a battery is. You have ions, usually lithium, that have to travel from one electrode to the other through a liquid electrolyte.
Right.
And that electrolyte is often held inside a porous separator.
So it's another tunnel system.
Very similar one.
Mm.
And just like in concrete, you have surface interactions. If those lithium ions get stuck to the walls of the separator, if that slow lane is too wide, the internal resistance of the battery goes up.
It charges slower, it gets hotter.
Exactly. So if battery researchers use this same simulation method,
They can design a separator to minimize that drag, to widen the fast lane for the lithium ions.
it's the exact inverse of what we want for concrete. In concrete, we want a traffic jam. In batteries, we want to clear the highway. But the physics you need to model it is identical.
Same physics, opposite goals. That's fascinating. What about the nuclear waste application? That feels like a much, much higher stakes version of the concrete problem.
It's the ultimate version. We store high-level radioactive waste in concrete casks or in geological repositories deep underground. The nightmare scenario is that radioactive ions, radionuclides, leak out and migrate through the pores of the barrier into the groundwater.
And you can't just wait 100 years to see if that happens. We're talking about time scales of thousands of years.
Tens of thousands of years. You have to predict that behavior. You cannot physically test it. You have to simulate it. You need to know with near absolute certainty how strongly those radioactive ions are going to stick to the pore walls.
So in that case, the stickiness, the slow lane effect, that's our safety net.
It's everything. We are banking on it. We want those ions to be trapped by the surface chemistry so they never, ever reach the biosphere. Gong and Chen's work helps validate those crucial safety models.
It's just wild to think the same computer code could help build a seawall in Miami, a better battery for a laptop, and a nuclear containment vessel in Finland.
It really speaks to the convergence of modern science. We're realizing that material science isn't a bunch of separate fields anymore. It all comes down to understanding the interface between solids and liquids at the nanoscale.
So bringing it back to the here and now, what happens next? Do construction companies start hiring molecular physicists?
I don't think your local contractor is going to be running these simulations on his laptop anytime soon.
Probably not.
But the big materials suppliers will. The companies that formulate the chemical admixtures that get added to concrete to change its properties, they'll use this.
So they'll be the ones optimizing the mix.
They can run hundreds of virtual tests. Instead of mixing 500 batches of cement and putting them in a saltwater tank for 5 years, they can simulate those 500 variations in a week.
It just accelerates the R&D cycle massively.
Which is what we need. The climate crisis doesn't give us the luxury of waiting 20 years for a better material. This kind of tool helps compress that timeline.
It really feels like we're moving from an era of discovering materials to one where we are designing them.
That's a great way to put it. For most of history, we found stuff wood, stone, and used it. Now we're tuning materials atom by atom for a specific purpose.
It makes the mundane world feel so much more complex. I'm looking at the sidewalk outside, and I don't see a slab of rock anymore. I see this chaotic, active filter.
And it's doing a surprisingly good job of it, thanks to those sticky, poor walls.
We've covered the method, the physics, the villainy of chloride, the global impact. Is there anything we missed about the specific mechanics? Any other little details?
Well, one detail we kind of glossed over is the difference between the sodium and the chloride ions. The study found they behave a bit differently because of their charge.
Okay.
The surface of the CSH is usually negatively charged. This attracts the positive sodium ions, but it repels the negative chloride ions.
But wait, if it repels the chloride, shouldn't that stop it?
You would think so. But what it actually does is it complicates the flow. It pushes the chloride ions away from the wall and into the center of the pore.
Oh, so the natural charge of the concrete inadvertently funnels the bad guy into the express lane?
In a way, yes. While the sodium gets held up near the sticky walls, the chloride can kind of surf the bulk water right down the middle. Understanding that specific interplay of charge, the electrostatic potential, is why the simulation is so vital.
Electrical drama in a driveway, who knew?
Physics is everywhere.
It really is. I want to leave our listeners with a final thought, something to chew on. We spent this whole deep dive deconstructing the illusion of solidity. We know now that concrete is this bustling hive of atomic activity.
A dynamic system disguised as a boring rock.
Exactly. So if concrete, the very symbol of hardness and permanence, is this active and this complex, what other solid foundations of our reality are we completely misinterpreting?
That's a heavy question.
I mean, think about the asphalt you drive on, the glass in your window, the plastic in your phone. We treat them all as static backdrops to our lives, but they are all aging, reacting, and flowing at scales we just can't see.
And if we could simulate them all with this level of detail,
Yeah.
what other huge problems could we solve?
Maybe the next big breakthrough isn't about inventing some brand new material. Maybe it's just about finally seeing the ones we already have with clearer eyes.
I think that's very likely.
Dr. Natarajan's article from Rice is linked in the show notes if you want to geek out on the specific details. It's really worth a look. Thanks for listening to this deep dive.
Until next time.